as the session chair said, my presentation title is Flexible Aluminium Nitride, Coupled MOSFET Device for Touch Sensing. I work on the tactile sensing area, and because tactile sensing or sensors find their application in many areas in our life, or in the industry, in a normal human, medical, everywhere. Majorly, you can see the tactile sensors in robotic, prosthetic, imaging, and other consumer gadgets, including the laptop and our mobile. One of the area in which I am focusing is for the robotics, because robots now are entering into the normal human life, so they need the electronic skin, and tactile sensors make an integral part of the any electronic skin. So if we see a robotic hand, because before deciding what kind of sensors to be used for a robotic hand, we need to study what kind of sensors are present on a normal human hand. And if we see just our fingertip in a 1 centimeter by 1 centimeter area, there are more than 1,000 or 2,000 sensors, tactile sensors like mechanoreceptors, which are present on our fingertips. So if we want to mimic the touch sensing capability which we have currently, we need to have a very high resolution sensors as well as a high speed sensor. That's why the sensor on which I am working is termed as a MOSFET. MOSFET stands P for piezoelectric, and Oxide comes from the MOSFET, so oxide semiconductor field effect transistor. The device, you can see that it is just a standard MOSFET, and over the gate we have one piezoelectric material. So for the functioning here, this slide shows how the device works. So we have a normal MOSFET currently, and when we deposit a piezoelectric material on the gate area and apply a pressure, the piezoelectric material produces charge, and that charge induces some change in the channel region of the MOSFET, and that change is read either as a change in the current of the MOSFET, or we can convert it as the voltage. Okay. So in the first run, we tried the PVDF-TRFE because it's a flexible piezoelectric material. It can conform to any substrate, so and it's easily processable. So that's why we use PVDF-TRFE. But the problem with the PVDF-TRFE was that it's a piezoelectric material. It's a very good piezoelectric material, but it's a pyroelectric as well. So it gives response to both pressure and temperature. So if my finger is hot, I have a fever. If I touch my sensor, then it will respond to both my force as well as the heat of the body, which is kind of a noise, because sometimes we don't want the temperature to sensitivity toward the temperature. So in the first issue was the sensitivity to temperature, and this has been recently published as in IEEE Sensor Journal. So in this work, what I did, we used nanoparticles of barium titanate. We mixed with barium titanate nanoparticle. Barium titanate is also a piezoelectric ceramic. Upon both have a opposite piezoelectric property, but similar pyroelectric property. So sorry. So we make a nanocomposite. A nanocomposite combines the good properties of both of them. So nanocomposite was flexible like PVDF-TRFE, and it has a higher piezoelectric property of coming from the barium titanate. Okay. And then we combine it with a MOSFET. So here you can see that to obtain the piezoelectric property from any polymer based material, we need to pole it. Pole it means we have to apply an electric field across the material to align the dipoles. And this mechanism or this property has been exploited to remove the or suppress the pyroelectric response. How we did it? Since they both have opposite dipoles, so upon polling we have performed a two-step polling. So first we just fold the nanoparticles, and then we fold the polymer, so that we just get the piezoelectric. And by polling we cancel the pyroelectric property of it. So we just make a simple capacitive structure of on a polyimide. This was the structure. So it has a aluminium bottom electrode, a composite as a dielectric, and a gold top electrode. By EDX and AFM, it has been observed that by addition of nanoparticle, we are not only suppressing the pyroelectric, but we are also enhancing the piezoelectric property. And we connected the extended gate here. And the response, you can see that it gives 670 millivolt per Newton sensitivity to the force, and sensitivity to temperature when both were applied together was just 7 millivolt per degree centigrade, which shows a significant decrease in the sensitivity toward the temperature. So now we solved one problem, but the second problem, which is basically this paper, is the polling, the requirement of polling itself, because the polling is a very high voltage procedure. So when we have, as you see the sensor structure, it has a MOSFET below the piezoelectric. So if we are polling the piezoelectric material, the high voltage applied across the material can damage the MOSFET itself. So there was a need of another material which can be used as a piezoelectric material over the MOSFET, but that does not require a polling. So one of the material was the aluminum nitride. Aluminum nitride, the advantage of aluminum nitride is that it's a non-centrosymmetric crystal structure. So there is something in the crystal structure itself which makes it inherently piezoelectric. It does not require a polling. The bad thing is that the piezoelectric coefficient is a bit lower as compared to PVDF TRFE, but still seeing the advantage that it cannot damage my device. Anyway, we can increase the sensitivity with the amplifier, but this requirement can be fulfilled by the aluminum nitride. So the next step was how to deposit aluminum nitride, because aluminum nitride, the issue with aluminum nitride is that it shows the piezoelectric property only when it grows in a certain direction. Certain direction, I means that when we deposit aluminum nitride, it can, by sputtering, it can deposit in a random crystal orientation, which is 001, 100, but the orientation which we want is just 002. So 002 gives the piezoelectric response. For that, this I already saw. For that, extensive process optimization has to be carried out, considering the process parameters, which is pressure, power, pressure of the chamber, so pressure of the chamber of the sputtering, what RF power we are going to give to the target, what are the composition of the gases which are in the chamber, and the temperature. The temperature we kept at room temperature because our substrate was polyimide, we did not want to damage it. We used classes 3 magnetron sputtering for it, and we sputtered it on a polyimide foil. These are the parameters which we use, so 700 watt, and these are the best recipes which I am showing here. We did many other process parameters as well. So after deposition, one of the way to know is that to know whether it has really grown in 002 orientation is to do an XRD. XRD, and if we see a peak at 36.1 degree, higher the peak, higher the better the piezoelectric material is. So we see a significantly high peak from here on polyimide. So it did have a piezoelectric properties. To check, we just attached in an extended configuration with a MOSFET. So for MOSFET, we did a new run for the fabrication with modified parameters. There were some issues with the previous design of the MOSFET, so new fabrication run has to be done. So this shows just a micro photograph of a chip which we fabricated. Response of the MOSFET just to check whether the MOSFET itself is working or not. And after connecting it to the aluminum nitride, we got the response. So we received the sensitivity. Since it is an extended gate, so we use a probe station plus a setup mechanism. So sensitivity we got 2.65 per Newton. So sensitivity here we define as a change in current, normalized change in current per unit force. So we got the sensitivity of 2.64. So with this, the summary, I'd like to say that here, okay, tactile sensor of course is an integral part of e-skin, and here I presented the two issues which currently we faced in the MOSFET. One was the issue to the sensitivity to the temperature, which has been solved using PVDF and titanate nanocomposite. Another work was the requirement of polling, which has been solved with the AlN. So these both work are characterized in extended gate format, of course. So future work will be focusing on direct deposition of these materials on the gate, because currently they are extended gates, so they do introduce some capacitance, parasitic capacitances. So if we directly deposit it on the gate, then the sensitivity is supposed to or expected to increase, because we will be reducing a lot of noise. Okay, so I'd like to thank the funding agencies, Marie Curie, European Commission, NEPSRC, and JWNC, and Fondazione Bruno Kessler. Thank you.